And welcome to a deep dive
Mm.
into something that sounds, deceptively simple, but
Mhm.
spirals into like mind-blowing complexity.
Yeah,
The Busy Beaver problem. Are you ready to like stretch those brain cells?
absolutely. It's one of those mathematical puzzles that seems almost playful
Right.
at first, but the deeper you go, the more you realize it has these like profound implications.
So let's start with the basics.
Okay.
Imagine a theoretical computer called a Turing machine,
Okay.
which basically operates with a set of instructions on an infinitely long tape.
Right. Picture a tape divided into cells, each holding a 0 or a 1.
Okay.
The machine has a little head that can read, write, and move along this tape. Think of it like a super simplified computer program following a very strict set of rules.
And the game, the Busy Beaver problem,
Yeah,
is to design a Turing machine that prints as many ones as possible on this tape
exactly.
before it stops.
And this is where things start to get really wild.
Okay.
Because
Got it.
as you increase the number of instructions this machine can have,
The potential number of ones it can print before halting,
yeah,
well, it just explodes.
it's not just getting bigger, it's growing faster than any function we can actually compute.
Right.
Faster than exponential growth, faster than anything you can, like, practically imagine.
That's the heart of it.
Yeah.
We use a special function called sigma of n to represent this, where n is the number of states
Okay.
or instructions the Turing machine has.
And we know the first few values.
Yeah.
A machine with one state can only print one, so sigma of 1 equals 1.
Right.
With two states, the maximum jumps to 4. So sigma of 2 equals 4.
That's right.
Then it's sigma of 3 equals 6, and sigma of 4 equals 13. Already getting pretty big, right?
But here's where we hit the wall.
Oh.
Sigma of 5.
Yeah.
The maximum number of ones for a 5-state machine,
Yeah.
it's unknown.
Unknown.
Yeah.
We have supercomputers, complex algorithms, all this amazing technology.
Right.
And we can't just figure it out.
It's not a matter of computational power.
The Busy Beaver problem is what we call undecidable.
Undecidable.
And that's because it's deeply intertwined with the infamous halting problem.
Okay, you've dropped this halting problem bomb a couple of times now.
Yeah.
Help me understand. What exactly does that mean?
Imagine you wrote a computer program and
Yeah.
you wanted to know with absolute certainty
Okay.
if it would eventually stop running
Mhm.
or if it would just loop forever.
Yeah.
The halting problem says there's no single algorithm, no magical test that can answer that question
Wow.
for every possible program.
So it's not that we haven't found the right algorithm yet.
Yeah.
It's that such an algorithm simply cannot exist.
Precisely.
Wow.
And to find sigma of 5, we'd need to analyze every possible 5-state Turing machine
Right.
and determine which ones halt.
Mhm.
But because of the halting problem, we can't do that. We're stuck.
So we're saying that even though the Busy Beaver function is perfectly well defined,
Right.
we can never know its exact values for higher numbers because it runs headfirst into this fundamental limit of computation.
That's the mind-bending part.
Yeah.
It forces us to confront the fact that there are things we can clearly define mathematically that are simply beyond our ability to calculate.
This is definitely challenging my assumptions about what's knowable.
Yeah.
It's like we've stumbled upon a mathematical concept that's somehow bigger than our ability to
Yeah.
fully grasp it.
It really does make you question, what we can truly know, doesn't it? And it's not just about the limitations of computers.
Yeah.
The Busy Beaver problem also reveals some profound truths about, infinity.
Okay, now you've really got my attention. We're talking about infinity now.
Yeah.
How does this relatively simple-sounding problem even touch on something
Right.
as vast and abstract as infinity?
Think about it this way. You could start counting from 1, 2, 3 and keep going forever, right? Never stop.
Theoretically, sure, though I'd probably need a snack break at some point.
Of course. But even if you counted forever, you'd never reach the Busy Beaver numbers for even moderately sized Turing machines. They're so large
Wow.
that just writing them down would take longer than the universe has existed.
So it's not just that these numbers are big, it's that they're practically inaccessible even with an infinite amount of time.
Exactly. It's
Yeah.
a glimpse into a kind of infinity
Yeah.
that's almost impossible for our minds to grasp. It's an infinity beyond counting beyond any practical measure.
Whoa, that's heavy stuff.
Yeah.
But it also makes me wonder, if the Busy Beaver problem is undecidable,
Right.
how do we even know the first few values of the function? How do we know that sigma of 4 is 13, for example?
That's a great question. We know those early values because we can exhaustively analyze
Okay.
all the possible Turing machines with a small number of states.
Mm-hmm.
For sigma 4, we've checked every single 4-state Turing machine and proven that none can print more than 13 ones before halting.
Ah, so it's like brute force searching through all the possibilities.
Yeah.
But as the number of states increases, that brute force approach becomes computationally impossible.
Precisely. The number of possible machines explodes exponentially with each additional state.
Right.
So while we can prove the exact values for small n for larger values, we're left with only lower bounds, like the 4098 we know for sigma of 5.
Okay, so we've got this undecidable problem touching on the nature of infinity and connected to the halting problem. Are you about to tell me there's even more to this rabbit hole?
Oh, there's always more to explore.
Oh, no.
Remember that concept we touched on earlier, Chaitin's constant?
Yeah.
It turns out that's also deeply connected to the Busy Beaver problem.
Right. Chaitin's constant, that mysterious number representing the probability that a random program will halt.
Right.
I remember you saying it's also uncomputable.
And here's how it ties in.
Okay.
The more states a Turing machine has, the more potential programs it represents. It's like having a bigger set of building blocks to create programs.
So more states, more potential programs, more complexity.
Yes. And the more complex those programs become, right?
The harder it is to determine whether they'll halt or run forever.
Okay.
This increasing complexity directly links the growth of the Busy Beaver function to the increasing difficulty of the halting problem, which in turn affects our ability to calculate Chaitin's constant.
Okay. I'm starting to see the connection here. It's like this tangled web of uncomputability.
Yeah.
But help me understand this link to Chaitin's constant a bit better.
Sure.
If it represents the probability of a random program halting, how does the Busy Beaver factor in?
Imagine you're picking a random Turing machine.
Okay.
I want to know if it halts. The larger the Busy Beaver number for a given number of states, the harder it becomes to determine if a machine with those many states will halt.
Because the higher the Busy Beaver number, the more possibilities there are for that machine to run for a very long time.
Exactly.
Making it hard to know if it'll ever stop.
Exactly. The Busy Beaver numbers give us a sense of how unpredictable Turing machines can be.
Yeah. Even with a relatively small number of states, this unpredictability contributes to why Chaitin's constant is uncomputable.
Right.
We can never know for sure what a sufficiently complex machine will do.
Wow. It's like the Busy Beaver problem isn't just about printing ones. It's about illuminating the very essence of what's computable.
Right.
And what's inherently unknowable in the realm of computer science.
And it doesn't stop there. There's another fascinating connection to explore.
Oh, boy.
This time to the world of mathematical logic and Gödel's incompleteness theorems.
Okay, we're going from Turing machines and infinity to Gödel now.
That's right.
This episode really is taking us on a wild ride.
It is.
But remind me, what were those theorems all about again?
Remember, Gödel essentially showed that within any sufficiently complex system of logic, there will always be true statements that cannot be proven within that system.
So there are things we know are true, but we can never logically demonstrate them to be true.
Exactly. And that's where the parallel to the Busy Beaver problem comes in. Just as Gödel demonstrated the limits of provability, the Busy Beaver function shows us the limits of computability.
So we've got unprovable truths in mathematics.
Right.
And uncomputable functions in computer science.
Yeah.
Both pointing to this idea that even our most powerful systems of logic and computation have inherent limitations.
It's a truly profound insight, and it's all connected to this seemingly simple problem.
Yeah.
Maximizing the number of ones a Turing machine can print.
This is blowing my mind wide open.
Yeah.
We've gone from a simple game to the limits of knowledge and infinity in just a few minutes.
Right.
What does this all mean? Why should we care about this Busy Beaver problem? It's like we've been staring at this deceptively simple problem, this Busy Beaver, and it's suddenly become like this window into some of the deepest questions about knowledge and infinity and the very nature of what we can know and compute.
It really highlights how interconnected these big ideas are. You start with a simple question about Turing machines, and before you know it, you're bumping up against the limits of logic and mathematics.
So if we can't actually calculate these Busy Beaver numbers for larger machines,
right,
what are we doing? What are the researchers who are fascinated by this problem actually working on?
Well, one of the main things they're doing is trying to establish better lower bounds for these unknown values.
Okay.
Remember how we said sigma of 5 is at least 4098?
Right. Because someone found a 5-state machine that prints that many ones before halting.
Exactly. So researchers are constantly searching for even more efficient machines,
Right.
pushing those lower bounds higher and higher. It's like a race to see who can build the most impressive Busy Beaver.
And each new discovery, even if it doesn't give us the exact value of sigma of n, tells us something about the incredible potential of these simple Turing machines.
Absolutely. And it's not just about finding bigger numbers. Analyzing the structure of these high-performing machines gives us insights into computational complexity itself.
So by studying these busy beavers,
Right.
we're not just learning about a specific problem, we're gaining a deeper understanding of the very nature of computation.
Precisely. It's like the Busy Beaver problem is a testing ground for our ideas about what computers can and cannot do.
But are there any practical applications for all of this? I mean, it's
Huh.
fascinating to think about these theoretical limits,
Sure.
but does it impact the real world in any way?
It certainly does. One area where the Busy Beaver problem has implications is cryptography.
Okay.
Remember how we talked about how the problem is undecidable?
Yeah, because we can never be absolutely certain if a given program will halt or not.
Well, that very idea of undecidability can be used to design more secure cryptographic systems.
Okay.
If you base your encryption on an undecidable problem, it becomes incredibly difficult for attackers to break the code.
So by harnessing the power of problems like the Busy Beaver, we can potentially make our data more secure.
That's one of the exciting possibilities, and it's a great example of how seemingly abstract mathematical concepts can have very real and tangible impacts on our lives.
Okay, so we've covered a lot of ground here.
Yeah.
We talked about Turing machines, the Busy Beaver function, the halting problem, Chaitin's constant Gödel's incompleteness theorems,
Wow.
and even touched on cryptography.
It's been quite a journey.
What's the one big takeaway you want our listener to walk away with?
I think it's this. Even in the world of pure logic and mathematics, there are still mysteries and uncharted territories.
Yeah.
The Busy Beaver problem, with its deceptively simple premise, reveals that there are limits to what we can compute and prove.
Right.
But it also inspires us to keep exploring, to keep pushing those boundaries, and to always remain curious about the universe and its secrets.
Beautifully put. So to our listener out there, if you ever find yourself feeling like you've got it all figured out, remember the Busy Beaver. Remember that there's always more to learn, more to discover, and more to wonder about.
And who knows? Maybe someday you will all be the one to make a breakthrough on this fascinating problem.
Thanks for joining us on this deep dive. We'll have some additional resources linked in the show notes if you want to explore the Busy Beaver problem further. Until next time, keep those brains busy.